thing that's really cool about this mission is there's nothing subtle about Deep Impact. It's something that anyone can understand. We're trying to smack a comet as hard as we can with a hunk of copper. We'll be going about 23,000 miles per hour, and we're going to watch what happens. And we actually get a surprising amount of excellent science data from this impact. We don't know what the interior of a comet is composed of. We don't know whether it's densely packed or loose, and we're going to learn a lot about that from this impact.
This is a first of a kind, and it's really exciting because what we're trying to do is not only hit the comet with an impactor spacecraft, but to also have a second spacecraft watching and seeing the impact at the same time and taking the pictures of the crater formation and getting the science data that's really behind this mission. So we like to equate that to a bullet hitting a bullet and another bullet trying to look at the same spot at the same time. Actually, we have amateur astronomers that are going to take part in observing the impact on Impact Day. Basically, if you're anywhere, say, in the southwestern United States, like California, for instance, and you have a relatively moderate-sized strength telescope, that you'll be actually able to see the impact. And depending on the size of the crater that it makes, you may be able to observe this brightness that occurs after impact for several days to a couple of weeks, depending on how long it takes the dust to settle back down. And we expect that it'll create a crater that will throw this dust up into the sunlight so we can actually get the pictures and the spectra of what that dust and material, that debris coming out of the crater actually is. Based on the cratering, when we actually smack this thing at 23,000 miles an hour, is you will get the basic properties of the comet and be able to apply that for future knowledge. You would be able to use that knowledge to understand how much and with what you got to hit one of those things to knock it off course. Now, this will not knock this comet off course, and it'll be like a gnat hitting a 747 airline.
Deep Impact is a remarkably quick mission as deep space missions go. It's only 6 months in duration. It's been a very intense period. We've got a great team on Deep Impact, and it's a very diverse group of people. And we've got people from the Jet Propulsion Laboratory as well as Ball Aerospace operating simultaneously from 2 different sites. We've got a lot of work to do, but we've got a great team to get it done.
All stations, this is Flyby Systems. We're approximately 21 minutes before impact. I'd like to do the final pre-impact status poll of all subsystems.
An ORT is an operational readiness test, and it's essentially a dress rehearsal of the flyby. It's the way that we make sure that we have all the sequences right, that we point the spacecraft in the right direction, that we have enough room on the hard drives on the spacecraft to store all the pictures, all the little details that have to be perfect, just like if you were doing a TV show or something.
Impactor telecom, what's your status?
The impactor will separate 24 hours out, and then there'll be a fairly quiescent period of 22 hours or so where the impactor is just is providing telemetry to the ground for ongoing monitoring and taking a number of scientific observations as well as navigation observations for post-encounter reconstruction. Then starting 2 hours out, 2 hours before the nominal time of impact, that defines the final targeting or the autonomous phase.
Well, it's a fairly complicated effort to try to get the spacecraft targeted and on course to impact the comet. We want to make sure we hit it. So at this point, the impactor takes over on its own, and it takes pictures of the comet as it's approaching. And then it will do propulsive maneuvers to basically fly itself into the comet. So we want to hit, obviously we want to hit the comet, and we want to hit it in a lit part. We don't want it to hit like on the dark side. So it's got to fly itself into a bright spot on the comet. And then this flyby spacecraft, which is going to be lagging behind at that point and take pictures of the impactor hitting the comet, it has to be pointed at the comet as well, and you can take pictures at the actual impact site.
We've got a high-gain antenna that we're pointing at the Earth, and so as we're moving the spacecraft around, we've got to make sure that we're moving the antenna in such a way that we stay pointed at Earth. So that's one of the challenges. Obviously, with our cameras, we're trying to follow what the comet's doing, and then with the antenna, we've got to stay focused on Earth. So that's definitely a challenge. Part of the spacecraft's turning one way, and the antenna gimbal's turning the other, and we've got to keep those synchronized and moving smoothly. And we're taking a bunch of images, we're storing those images to the non-volatile memory boards, and one of them actually fills up, so we get to 95% capacity on that board, and then we start writing to the other board. Those images are coming fast and furious, and at the same time that we're storing them, we're CFDP downlinking them to the ground. So all that stuff's got to go on at the same time. The processor's working overtime, we're storing data rapidly, downlinking data rapidly.
This is Flyby Telecom. The Flyby Telecom is
Flyby Instruments, what's your status?
It's not a sure thing. I mean, doing stuff like this is incredibly difficult. I mean, we have to fly this little tiny spacecraft to this comet. We have to fly it within a few kilometers of where it needs to go. It's not a trivial thing.
Well, we've had several spacecraft fly by comets and take pictures as they went quickly past. The first was the Giotto spacecraft back in March of 1986, and we had the Deep Space One spacecraft fly quickly past Comet Borrelly. The Stardust spacecraft flew quickly past Comet Wild 2 and picked up some dust samples to bring back to Earth. But as they're all quick flybys, so you have to take pictures as you go by very quickly, so you don't get a chance to study the comet. And you certainly don't get a chance to understand what's in the inside of a cometary nucleus. And that's, of course, what the primary science goal for the Deep Impact mission is. What is a comet made of? How is it put together?
The impactor for Deep Impact is a fully functional spacecraft. It's not just a cannonball. It's got a camera on it. It has a propulsion system, attitude control system, spacecraft computers, all those things that you traditionally think of as part of a spacecraft. If you were riding on the impactor, you're approaching the nucleus at 10 kilometers per second, or a little over 6 miles per second. Ultimately, half of the impactor mass is copper, and that corresponds to approximately 45,000 pennies. We have a prediction that we will excavate a crater the size of a football stadium in about 200 seconds. However, the research community disagrees on the nature of comets, they disagree on how they're held together, and they therefore disagree on what the cratering process will do, and therefore on what kind of a crater we'll get at the end.
Well, there's a couple of scenarios that could play out when the impact occurs. If the comet is solid, like a solid ice ball, like a block of ice you might take out of your refrigerator and put in your drink, if it's that hard, then the crater will be relatively small, just 10, 20 meters in size, and it will form rather quickly. On the other hand, if it's a fragile object, sort of like a souffle or the foam on a cappuccino or something like that, we're expecting a much larger crater, and it's going to form more slowly over a few minutes. But either way, we're going to know how the comet is put together. Comets are not only important for understanding how the outer solar system formed and how life, the ingredients of life were brought to Earth, but they may well be important for future space exploration. In the coming decades, when we start to send manned spacecraft out into the inner solar system, we're going to need water, and comets are about half water ice to survive, and we're going to need rocket fuel. And comets, of course, water is hydrogen and oxygen. And if you can break the water down into hydrogen and oxygen, that is the most efficient kind of rocket fuel. So in the future, comets may well be the watering holes and the fueling stations for interplanetary travel.